Good day, everybody. This is a review of signals and systems. The class objectives, the material that we're going to cover, includes the signal size. We talk about energy, power, root mean squared. Then we go into signal classifications, signal operations, and we cover some important functions like the Dirac delta function and the step functions. The size of the signal. Now, given a signal, how do we characterize this signal? So, for example, we have three signals here. If you want to characterize this signal, if you want to describe this signal, so how do we measure this signal? Do we talk about the amplitude? Because this one has more amplitude. Is it really a bigger signal? Should we use the amplitude as a measure for comparing signals? Or should we use the area? If you look at the area, then this has a positive and negative area, which concludes a zero size. So amplitude or area might not be a very good measure of a signal. What engineers usually do, they use energy and power. So what is the definition of the signal energy? Mathematically, we can define the energy in a signal as the area under the square of the curve. And in general, we have absolute value with the square because the signal itself could be complex. So it's like somebody would say, why do we have square and then we have absolute value? And in general, if you have a complex signal, you need to find its magnitude and then you square. And then you find the area. It's like the area under the square of the curve. Now, the signal power, it's very important to distinguish the energy from power. We can think of the power as the rate of use of energy. So we can formally say the average power is the time average of energy. When you look at the mathematical representation, now you have a very similar definition for the energy, but then you have to divide by time. So you cover a certain period, how much energy in a given period, divide by time. You can start from minus t over 2. If your signal is periodic, capital T would represent the period. So integrate from minus t over 2 to plus t over 2. This is one full period, and you divide by t. You can go from minus t to plus t, divide by 2t. It's very important to make sure that you divide by the time, which is considered in the integration. Now, not all signals are periodic. To make sure that the definition is generic, we have to take the limit as capital T goes to infinity. If your signal is periodic, you don't need this limit because it's just going to be repetition, so we can take only one period. But to generalize, we need to take the limit as t goes to infinity. Now, from this definition, you can see that the power is defined to be the mean squared value, because if you take the integration and divide, it's like you sum and divide by the total number, you get the mean value. But it's not the mean of gt, it's the mean of the square. Now, if the power is the mean squared value, what will be the root mean squared value? It will be the square root of the power, the RMS value, the root mean squared value. Here are a few comments I'd like to share with you. The first one is that to find the power, the signal has to be periodic. Otherwise, you have to take the integration to infinity. Again, very important note, power and energy depends on the load. In real life, if you have a signal, voltage or current, energy and power will only or can only be calculated if you have a certain load. But what we do here assume that the voltage and current are applied to 1 ohm resistance. That if you take the signal across 1 ohm resistance, then you get this much of power and this much of energy. However, if you change the load, then you don't get the same power from the same signal. The unit for energy and power is joules and watts, and some books, some textbooks, they just assume they write watts and joules. This is not very correct because unless you have a load,
here are two
examples.
examples
That the load is 1 ohm. To find the power and energy, it says in the question, find or determine a good measure for the following two signals and evaluate it. Is it the power or energy? If you look at the signal on the left, then we can see that the area under the square of the curve is limited. So we can think of energy The energy is defined to be the area under the square of the curve. This is the general definition. Starting from the left, we have 0 energy here. Then from -1 to 0, the square of the signal is 2 squared because we have 2 here. For the second part of the signal, then we have 2 e to the power minus t over 2. If you square that, you get 4 e to the power minus t. Executing the integration of these two should be no problem because we have constant or exponential. The first term will give you 4 and the second term will give you 4. The total should be 8. For the second signal, which is periodic, a good measure is to use the power. And by definition, the power is defined to be 1 over 2 because the period here is 2. Okay, the time it takes for the signal to repeat itself is 2. Okay, you can integrate. It's easier to integrate from -1 to +1. The function here is clearly t. Okay, it's a straight line. We should be able to represent this line as t with slope equal to 1. So the square of that becomes t squared. So executing the integration again, you get t cubed over 3 and then substitute. The final answer should be 1 over 3rd. How much is the energy here? The energy is the area under the square of the curve. If you square this curve, it goes from -infinity to infinity. So the energy for this one would be infinity. So for finite signals, it's finite area signals, it's better to use energy. For periodic signals, it's better to use the power as a measure. Here is another example. This example is important because it deals with the sinusoidal signal, the tone. So a signal g of t defined to be c, a constant amplitude, cosine omega naught t, this is the angular frequency, and this is a phase. So how much is energy or power in this signal? If we apply the definition of the power, so this is the integration, we have the square of the signal, and then with the cosine square, we can split this into 1/2, 1 plus cosine double the angle. Everything here remains the same. Cosine square, we use the identity of 1/2 times 1 plus cosine double the angle. Now we have two terms now for the integration. For the first term, we split the first term. We can easily integrate this. The second term is an integration of a cosine signal over not just one full period, over 2 periods. Remember here now the frequency is doubled, which means we are integrating over 2 full periods. So cosine over 2 full periods will be, of course, 0. Remember, cosine has positive and negative terms. So this integration will be simply 0. The integration of the first term is nothing but c squared over 2. It's c squared over 2. So the t will cancel, and what remains is c squared over 2. That's the power of a sinusoidal signal, is amplitude squared over 2. It's irrespective of the phase or the frequency. Once you know the power, by definition, the RMS value is the square root of the power. So it becomes c, the amplitude, over square root of 2. Important notes: if you have multiple cosines and you want to find the total power, if they have different frequency, then all you need to do is the sum of the individual powers. So power add up for sinusoidal signals of different frequency. But this is not true in general. If you add 2 signals, the total power does not equal to the sum. And this is a special case where we have a cosine and cosine, 2 different tones with 2 different frequency, then you can add the power. Other important signals, we consider the sinusoidal here. If you have a DC, a constant value, then its power, if you apply the same rules, you get c squared, and the RMS value will be just c. I'm putting this in a box because these are 2 important repeated functions, sinusoids and a DC, a constant value. We don't have every time to apply the formula. Now, having found the energy and power, now we can look at different classification of signals. Signals can be classified as being analog versus digital. Analog signal take any value on the amplitude. Digital signals take discrete values. That's with respect to the y-axis. Similarly, for the x-axis, for the time axis, we can have continuous time versus discrete time signals. We can have periodic signals or non-periodic signals. Periodic signals, f of t, will repeat itself, so it's equal to itself after a certain shift. This shift is the period. So the signal itself repeats itself at multiples of that period. We can also classify signals as being deterministic versus probabilistic. Deterministic signals can be computed mathematically or graphically. You can tell what comes next, like sinusoidal signal. But for probabilistic signals, you don't know what comes next. You have no idea. So for example, for this signal, okay, if I ask you to sketch what comes next, it's a random signal for us. So 1, 2, 3, 4 different ways of classifying signals. Finally, we also have the energy versus power signals. Energy is a quantity and power is a quantity, but we can use it also as an adjective. I can say this is the energy of the signal and the power of the signal, or I can also say that this is an energy signal or a power signal. You can calculate the energy in a certain drink, or you can say that this is an energy drink, where you are using this as an adjective for the drink. That's the same for signals. Now, so when do we say a signal is power, and when do we say a signal is energy signal? Energy signals have the following characteristics. The power in energy signal is always equal to 0, and the energy should be finite, between 0, and it should have finite value. It should be less than infinity. On the other hand, a power signal, it is similar definition, but the energy here goes to infinity. The power itself is finite. We call it power signal because the power is finite. But notice here we are excluding the equal sign, because if we make it equal sign, then all power signals will also be energy. We want to make them distinct. This is why energy signals have finite energy, power signals have finite power. But here we have equal sign, and here we have no equal sign. And this is why we're saying a signal cannot be both power and energy signal at the same time. This is like the ramp signal. The ramp signal is not an energy signal, and it's not a power signal. Both definition does not apply. All right. Now, in general, usually periodic signals are power signals, and non-periodic signals are usually energy, but not always, as I mentioned. The ramp signal is one example. Any signal that has limited power and it's time limited is an energy signal. Usually energy signals have a confined area, and it's easy to distinguish them. Now, every real-life signal, we can think, if you want to be exact, every real-life signal is an energy signal, because, there is nothing like infinite energy. Every real-life signal is energy signal, because there is no infinite power. Because for a power signal, the energy goes to infinity. So again, every real-life signal is an energy signal, because a power signal requires infinite energy, which is not, of course, the case in real life. But we can approximate. If things start to repeat itself within a given time, we can say it is a power signal or energy signal. Example, determine if the following signal is energy, power signal, or neither, and evaluate its energy and power. This is a sinusoidal signal. You can tell directly that a sine or cosine, the difference is just in the phase. So the power of the signal is amplitude squared over 2. You can start from scratch, or you can find the power directly. The power is amplitude squared over 2. It's 9 over 2. And of course, the energy the area under the square of a sinusoid is infinity. Either you apply the formulas, or you can just conclude directly. All right, now, next, we look at some useful signal operations. Given a GHT signal, how do we shift the signal, scale it, compress it? And just to recall quickly, we can apply time shifting. A signal of t can be shifted to ft minus a certain value, capital T. If this is positive, then we are shifting to the right. If we have, t minus 5, then we are shifting to the right 5 units. If it is negative, remember that there is a minus sign here in the formula. So if it's negative, then we have a shift left. We are shifting right or shifting left by changing the time operation. If we scale the time by a certain constant, A, then if this constant amplitude is greater than 1, that's 2, 3, 4, 5, minus 3, minus 4. If it is greater than 1, then we have compression. If it is less than 1, then we have expansion, like 0.5t or 0.25t. Now, if in addition to the amplitude, it has a negative value like minus 5 or minus 2 or minus 0.25, this impact of negative will cause time reversal or time inversion, as we're going to show with examples. Now, we can have combined expansion and inversion at the same time by scaling by minus 5 or minus 0.25. So this shows you the original signal, the compressed version of the signal, and the expanded version of the signal. Time reversal means whatever in the left side of the x-axis will be flipped to the right and vice versa. So the flipping is around the y-axis. This is time reversal. Also can operate on the y-axis, so that these operations happen on time. We can also operate on the magnitude or amplitude of the signal. If you add c, a constant to the signal, then we are shifting up. If this is negative, we are shifting down. We can also scale the signal by multiplying by b. Again, similarly, if the amplitude of this is more than 1, then we have amplification. If it is less than 1, we have attenuation, making the amplitude smaller. And if it's negative, we have inversion around the upside down. Okay, so we have different operations. These red ones are on the x-axis time, and those operations are on the y-axis. Example of time operations. I pick one relatively combined example because it's easy to do shifting or reversal. But what if we have combined operation, like f of t is shown here, and you are asked to sketch 4 minus 3f minus 2t minus 6. We'll focus on the time because the operation outside are relatively easy. This is shifting, this is scaling and inversion. But what happened here, because we have combined operation, what should we do first? Should we shift first or scale or invert? To avoid this confusion, we're going to do time mapping. So this blue part of the signal, we'll keep it on the side, and we'll focus on the time shifting. The time has changed from t to t prime. So t prime is now equivalent to minus 2t minus 6. Okay, if we make a small, if we solve for t, then we take plus 6 here, we divide by minus 2, and we get a new relation. We can tabulate this into the table, a small table. So we're trying to map what would be the new t given t prime is given values. So I'll pick the important values. We have one important value at minus 2, minus 1, and plus 4. You can pick more values. So I want to know where this is going to be mapped. So I filled my t prime minus 2, minus 1, plus 4. Now I will substitute in this equation. So at minus 2 plus 6 is minus 4, plus 4, divided by minus 2, it's minus 2. So it says that this point, which was minus 2, will be mapped to the same point. Minus 1 will be mapped to this, 4, and minus 5. So we can make a small sketch where we show that these points, minus 2 is the same. The one that was minus 1 is now mapped to minus 2.5, and so on. You can see that this function is now the following new function. There is some compression shifting. The beauty of doing it this way, you avoid the requirement for the sequence which one to do first. But you can also do it in a different way. So now once we are done with the shifting, we can continue the scaling and shifting up. Okay. The question here said, this is an exercise where if you want to practice, it's not too difficult given the following sketch of g of t. This is in fact a reverse operation, reverse question. What you see here is g of t minus 3 divided by 4, and your job is to sketch g of t. So the previous example, I was given g of t, and I am asking you for some operations. Now what if you know that this is the shifted or manipulated function and you want to recover the original signal? Okay, now we can do the opposite operation. So t now is mapped into 2 prime minus 3 over 4. Alright, and now the important values are 0 and 2. We don't solve like we did before. You just substitute and we got the original time stamps, so we can recover the original signal. Once again, the difference between this example and the previous one, we are given the shifted version of the signal and we want to recover the original signal. So we don't need to solve for t prime here. Okay, now let's finish here with some important functions. The first one is the impulse function. It's also known, the unit means it has an amplitude of 1. It's an impulse function because we will have also pulses. When I say impulse, it's a different thing. It's an impulse function. It's also known as a delta function or Dirac delta function. This is the name of a scientist. We're giving credit by saying Dirac delta function. Here how it looks, here how it's defined. The unit impulse function, delta of t, satisfies the following conditions. Okay, it's equal to 0 for all values of t does not equal to 0. And it's not defined at t equal to 0. We're not saying what it has in terms of value at t equal to 0. But we are saying it's equal to 0 outside. Like this is the delta function. It's always 0 here for t does not equal to the specific time instant. We're also told that the area under the delta equal to 1. Area always equal to 1. So what you see in this figure is an approximation of delta function. We can approximate the delta function as a square, goes from minus epsilon over 2 to plus epsilon over 2. If you want to make it, if epsilon goes to 0, then this dimension will shrink, and we have to maintain the area of 1. From here to here we have epsilon, so the height must be 1 over epsilon. Epsilon times 1 over epsilon guarantees an area equal to 1. If you shrink the width here, make it smaller, then the height automatically goes up. If this goes to 0, the height goes to infinity. So here's some properties of the unit impulse function. If you multiply it by if you multiply the delta function by any function, okay, then we get the function evaluated at t0. Why? If you look at this curve, here is any dummy function. You multiply it by d, a function shifted to a certain value t0 or d. The multiplication will always give you 0 outside. So the function will not be important except at that instant. And this is why the entire function here drops, and all I have is a scaling by the function evaluated at t0. So this makes things simple because a function that is a function of t is now converted into a constant. Now, things would be even easier if we have integration, because once you have integration, we have what we call the sifting or the sampling property. Let's derive it quickly here. This is delta multiplied by a function. We are integrating. Using the first property, now we can substitute t0. Now we have a constant goes outside. The area under the delta is nothing but 1. So we get f t0. Here is an example. Delta multiplied by f of t. The shifting is 0, so I can substitute 0. It goes outside as a constant, and I get f0 at the end. So comparing these two properties, because they are usually confused, adding integration will make things easy, because without integration you need to keep the delta. But with integration, what remains is just the function evaluated at specific time. Now, we also have the unit step function. Okay, I'm sure you are familiar with this. This is just a quick review. The unit step function is defined to be 0 for everything before 0, and it's 1 after that. So just to be careful here, our book or our reference is defining the ambiguity at t equal to 0 to be equal to 1. So we have greater than or equal here. Some different books, they define it different ways. So what's important is for less than 0 we have 0, and for more than 0 we have 1. It's like a step function. Okay, now the relation between the step function and the impulse function, if you integrate from minus infinity to t, not to infinity, because remember that integration to infinity give you 1. So integration from minus infinity to t give you the unit step function. And vice versa, the derivative of unit step function give you the delta function. Okay, it's also good to know, as part of your review, the meaning of causal signals and causal systems. Causal signals, they are only defined for positive time. Causal systems, in causal systems, the output always starts after the input. This is saying it in simple words. If you want the mathematical background, then you can visit the issue of causal signals and systems. This is good enough as background in terms of signal systems for us to proceed with communication topics. Next, we'll talk about Fourier series and transform.